on entropy. All right, so getting started. Today will be our first lecture on chapter 3. We'll spend some time look at what is the second law of thermodynamics. Remember, like what we did for the first law, we're not going to do like proof of the second law of thermodynamics. It is a law. It is like we just accept it as true. Our goal in this class is to understand what is the second law of thermodynamics and how to use the second law of thermodynamics to solve problems that we care about. All right. And later this lecture, we'll spend lots of time talking about heat engine and also cycles. Well, we'll first talk about what is a heat engine, what defines the efficiency of a heat engine, and then we'll use our second law of thermodynamics to prove something called Carnot principle, and then we'll look at Carnot cycle. So, getting started on our first goal of today, which is the second law of thermodynamics. So we'll read these laws together, and hopefully it will make sense at the end of chapter 3. So right now it's going to be, well, let's just read it together. And some of the terms might not make sense to you, but it's okay. We'll talk about them. So I have two different ways to talk about the second law of thermodynamics. The first one is called a Kelvin-Planck statement of the second law of thermodynamics. It reads, it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat into the system from a heat reservoir and the performance of an equivalent amount of work by the system on the surroundings. I know it's super long. Translate into plain English, what it means is imagine we have a cyclic machine. We'll talk about what a cyclic machine is. Imagine we have a cyclic machine. This cyclic machine cannot completely convert the random molecular energy of heat into ordered motion of mechanical work. All right, so if you think about what is heat, when we say heat transfer, that means we have a transfer of energy. But the nature of heat flow, they are random mechanical energy. They have like different directions, right? It's a form of energy, but it's not like work. Say if we have mechanical work, say we push it into some direction, right? We're doing work. In that process, the mechanical work we're doing, that's directional, that's ordered. So what the second law of thermodynamics said in this interpretation is that a cyclic machine cannot completely convert heat into work. We have a different way to say it in the Clausius statement, which say it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat into the system from a cold reservoir and the flow of an equal amount of heat out of the system into a hot reservoir. That's like the similar kind of thing we were saying. It's like instead of you cannot convert completely random energy of heat flow into work, you also cannot 100% preserve the heat that's being transferred from hot to cold back from cold to hot. I know when the first time I read this statement, that's exactly my face. I'm like, what is going on, right? So again, we'll come back to them and try to use these laws of thermodynamics into specific physical chemistry problems that we care about. So getting started, we'll first introduce the idea of heat engine. So what is heat engine? Whenever we see this definition, we'll just read it together and see if there are any terms you don't know what it means. So heat engine converts some random molecular energy of heat flow, so it converts heat, or Q, into ordered macroscopic work, or W. All right, so a heat engine converts Q into W. Alternatively, you'll also see our textbook say something like a heat pump. Let me use a different color. So a heat pump would be we input energy into the heat pump, and then we transfer energy from a cold reservoir to a hot reservoir. So it's just the reverse version of the heat engine. or on the graphic picture, what exactly does a heat engine do? So in here, we imagine we have a hot reservoir, say hot water or hot oil, that's at higher temperature. So this one is the thermodynamic temperature, just our textbook called temperature in different symbol, but that's just temperature. Right, so from that hot reservoir that's at higher temperature, it transfers heat into my heat engine. So now my heat engine is the system we care about. So surrounding transfer heat into system, my QH is positive. All right. Now, part of that QH got passed through the heat engine and being transferred into a cold reservoir. So that part of energy is transferred from my system, which is my heat engine, into the surrounding. So my QC is a negative. So in this figure, we're just manually set QH, QC, and W all be positive number. And we tell you their sign by inserts like a negative sign in before. And in this process, our heat engine will convert part of the energy difference as work. So system is doing work on the surrounding. This is our work output. Also negative. All right. So for this kind of heat engine, what we care about is how much work this heat engine can do, given the amount of heat input into the engine. Or the other way to put it is we can define the efficiency of a heat engine as E equals to work output per cycle over energy input per cycle. Now, since my work output per cycle is like a negative number because the system is doing work on the surrounding, we want it to be like a positive number. I don't want my efficiency to be a negative number, which is confusing. So typically, people use the absolute value of work over QH as our definition of efficiency of a heat engine. With me so far? So we went over the what is a heat engine, what is the setup of the heat engine, what are the signs of heat transfer and work that's taking place at the heat engine, and we define efficiency of the heat engine. So now we want to take one step further to think about how can we use our definition of efficiency in combination with the first law of thermodynamics. So, what do we know about the first law of thermodynamics? We have delta U equals to Q plus W. All right, that's just generally true if we're considering our system. The change of my internal energy is, well, Q plus W. And now imagine we have a cyclic process, meaning like we start from an initial state, we run our cycle, and then we can run our cycle backwards. So we're back into our same initial state. Or we have like a heat engine and a heat pump working in a cyclic process. All right, so like a heat engine and a heat pump. The heat engine absorbs heat from the hot reservoir and then do work on the surrounding or on the heat pump. And the heat pump use the work output and then go back to the original state. So we're having a cyclic process. So imagine a cyclic process. We have delta U equals to 0, right? And again, the reason delta U is 0 is because internal energy is a state function. And for cyclic processes, the changing state function will vanish to 0. And then what do we know? So for this process, if delta U equals to 0, we can write our negative W equals to Q, while the total heat transfer is QH plus QC. all right? And by moving the terms, or divide both sides of this equation by QC, we got negative W divided by QH, sorry, dividing both ends by QH equals to 1 plus QC over QH. And recall our definition here when we talk about efficiency. This one is effectively our definition of efficiency. We end up getting E equals to 1 plus QC over QH. So looking at this equation we derived, now this math is not hard, but thinking about what exactly does this equation tell us? We have efficiency of any cyclic engine or cyclic machine, right? For any cyclic machine, we have the efficiency of these machines can never be exceeding 1. So it's 1 plus QC over QH. Now QC is the heat flow from the engine to the cold reservoir. QH is the heat flow from the hot reservoir to the system. Or vice versa, you can think about a heat pump. It works the same. My QC and QH must have different sign, right? Because one of them is going in, one of them is going out. So the take-home message here is the efficiency of any cyclic machine must be less than 1. Must be well, you can't have a machine that's 100% efficient. This also fits our expectation from the second law of thermodynamics. You cannot have a machine that's a heat engine, right? That's 100% taking the heat and transfer it into work. So efficiency must always be smaller than 1. We'll come back to efficiency later on and calculate the efficiency of a specific cyclic process. But before we do that, I want to take one more step and thinking about what is the maximum efficiency we can get. So, in this case, we want to use our second law of thermodynamics to prove something called Carnot's principle. Reading the Carnot's principle together, what it says is that the maximum amount of work from a given supply of heat is obtained with a reversible cycle or reversible engine. So a reversible engine pretty much tells us, now remember the previous engine is heat flow into the engine, and then we output work and then QC. Right? Imagine now we run the engine backwards. We input work and input QC and output QH. So in a reversible engine, there will be no change in the number of those QC, QH, and W input and output. You can run it forward or backwards. So that's the definition of a reversible engine. But now let's think about it. What does it mean by maximum amount of work from a given supply of heat is obtained with a reversible engine? And can we prove it with the second law of thermodynamics? All right, so remember the question we're trying to prove is the reversible engine gives us the maximum amount of heat possible. So I'm gonna go super slow on this one and just raise your hand whenever you feel like you're lost. So in here, we're trying to prove that my reversible engine is the most efficient one. Now, whenever we're trying to prove something, we want to set up, say, what if we have a super engine, which the super engine's efficiency, E super, is larger than E reversible. All right, and we set up this cycle to a way that my super engine is a heat engine, so it absorbs heat from this hot reservoir. We call it QH super. It does work. We call it the W work super. and then also output heat into my cold reservoir, like QC super. That's the right hand. On the left-hand side, we have a heat pump, right? Like what we just said, heat pump is the reverse of a heat engine. So in this case, it takes W reversible as input. It also takes QC from the cold reservoir. And it outputs negative of QH reversible. All right, so first step, we discuss what exactly are the two engines of interest that creates this cyclic process or a machine. Next up, we can manually set the rate of these engine so that my QH reversible and QH super have the same magnitude, or the total internal energy of my hot reservoir doesn't change by alternating the magnitude of QH reversible and QH super. Is this color okay for you? Yes.
I have a question. Is one of the QC negative or
Yes, this one should be negative. Thank you. Yeah, and let's just manually set the magnitude of my QH reversible and QH super to be the same. So we have negative QH reversible equals to QH super. And now let's look at what does this machine do in this kind of setup, right? So first of all, we set up this cyclic machine. And now we're ready to analyze what this machine is doing. So remember our definition of efficiency. So E is defined to be the absolute value of work over QH. All right, so because we manually set the value of these QH to be the same, what we're saying is my W super is larger than my W reversible, and also taking this efficiency together. So one thing you might be confused, because you'll be like, this one is negative, right? How come my QH, we use QH here? So remember, this machine, the left cycle, the heat pump is a reversible cycle. So we can flip the direction of that cycle so that my QH is remain the same magnitude. Okay. So the conclusion here is if my original hypothesis that E super is larger than my E reversible, then the magnitude of my work super must be larger than my work reversible, using the definition of efficiency. And now we have a problem, because if my W output super is larger than my work reversible, then this cyclic machine will end up to be able to provide a net work output. All right. So in this kind of hypothetical setup, if the efficiency of my super engine is larger than the efficiency of my reversible heat engine, we will have a machine that outputs work. And going back to our original statement of the second law of thermodynamics. So I'm going to put it back here. And let's read this again. When we say a cyclic machine, Now that's the cycle we just defined with a reversible cycle and a super engine. Cannot completely convert the random molecular energy of heat flow into ordered motion of mechanical work. Now, in the cyclic machine we just set up, the only thing that's happening in the cycle is the flow of heat. So this machine should not be able to convert this heat flow into a net work outcome. And hence, this machine violates our second law of thermodynamics, meaning that we cannot have a super engine whose efficiency is larger than a reversible engine. And that's what the Carnot principle is saying. All right, so the maximum amount of work from a given supply of heat is obtained with a reversible engine. Let's see if we have any questions on this part. Again, what we're trying to do here is using something like a law of thermodynamics and to use that as a tool for us to prove a concept and find out something of real interest, because we want to have a heat engine that is as efficient as possible. We want to transfer as much energy from heat into something we can use, which is work, as possible, right? So that's our steam engine. So that's just of some real interest, and one of the reasons we want to study thermodynamics. Okay, any questions? No? Okay. Let's move on to our next topic. So we went over the general definition of heat engine and also the second law of thermodynamics. Now let's, again, looking at a simplistic possible scenario and try to derive information from our setup. So I think I made a mistake here. Let me just correct it really quick. One second. It's a very ugly drawing. I'll replace it with a prettier one later. So in this drawing, imagine we have the cyclic process that we call Carnot cycle. So in a Carnot cycle, what we have are all reversible processes. So remember we discussed a reversible cycle is the most efficient cycle. So we want to have reversible cycle to get started. We'll first introduce what is a Carnot cycle, what is happening in Carnot cycle, and how do we calculate the efficiency of a Carnot cycle. All right, so getting started, what do we have in the Carnot cycle? Let's see, we have 4 different thermodynamic states with different temperature, pressure, and volume. And what is happening between these 4 thermodynamic states are 2 isothermal processes and 2 adiabatic processes. Or effectively, you can imagine what happened is we start from a hot temperature at certain PV. We have an isothermal expansion where the volume and pressure changes, but temperature keeps the same. Then we have an adiabatic change of temperature. So even if my Q is 0, we can have an adiabatic change, decrease of temperature by alternating pressure and volume. And then have another isothermal compression at the same TC, and then undergo an adiabatic process to go back to the original state. So what exactly is happening in that cycle? So let's do that on the board together. So typically, when analyzing our Carnot cycle, we will plot what is happening on a PV diagram. So So in the typical PV diagram, on the y-axis, we have pressure. On the x-axis, we have volume. And then, that's our starting, 0. So let's say we have our first step, which is at TH. Let me call this like state 1. The first process that's taking place is an isothermal expansion. Now, isothermal expansion tells us, well, the volume is increasing. My temperature remains the same. And to simplify our discussion, let's just say this is an ideal gas. It's also true for other systems, but just for now, let's stick with ideal gas. But we have like TH stay the same at my point 2. My volume increase. So how will my pressure change? The pressure will decrease. Right? So we have our second point. Now, on my lecture note, I linked these points with like straight line. They're not necessarily straight line. They can be like, in reality, they are curves, but that's just for demonstration. So this line is an isothermal expansion. Right, so temperature is kept the same along every point between my point 1 to point 2. Secondly, we have our third state where the temperature is at Tc. Let's say Tc is smaller than Th. C referring to cold. Now the question is, where is my Tc on the diagram, knowing that between 2 and 3, we have an adiabatic process. So we did this, there are different ways to do it, right? So last lecture, we went over the adiabatic process of an ideal gas. So we can actually solve for what is volume, knowing what TH and TC and what is my initial volume is. So that's my T2 over T1 equals to negative V1 over V2 NR over CD. So we know like volume will increase when my temperature decreases. For the adiabatic process between 2 to 3. All right. You can also solve this by just using intuition. There are different ways to do it. Again, for adiabatic process, we need know that Q equals to 0. And since we have Q equals to 0, my delta U equals to W reversible. Right, so for ideal gas and also for reversible processes, we have W reversible equals to negative PdV. So since my temperature is dropping, my delta U is a negative number. So final minus initial is negative. And here we also have a negative, so my dV must be positive. Yes. So my dV, the change of volume, must be positive. All right, so different way to solve the problem, but it'll give you the same results. All right, so now we're here. We have state 3, and then we want to have another isothermal compression to go to our state 4. The same logic, what we had before. This is a isothermal compression. And this should be a little bit higher. And then later on, we finish the cycle by go back between our state 4 back to state 1 to complete the cycle. So definition, whenever we see a Carnot cycle, what we are saying is this cycle involves two isothermal processes and two adiabatic processes. Also, for any Carnot cycle, for all Carnot cycle, they must be reversible. Meaning like it's the same to run it from 1, 2, 3, 4 to like 1, 4, 3, 2. Well, it gets the same answer. It's like reversible. It doesn't matter which direction you run it. So now we have set up our Carnot cycle. Our next question becomes, what is the efficiency of our Carnot cycle? Right, so we have irreversible equals to 1 plus QC over QH. So that's the one we derived earlier today. And let's look at how to further simplify our irreversible into something we can measure. Right, so QC and QH are not very straightforward to measure. What we have are like temperature, pressure, and volume on my Carnot cycle. So how do we translate this equation into something we can measure? That's our goal for the next step. All right. Again, so the goal here is to calculate the efficiency of my Carnot cycle and use this calculation to demonstrate that the irreversible or the efficiency of a reversible engine only depends on the change in temperature of the reversible engine. Or say this irreversible is a function of TH and TC. And let's think about what is that relationship between the efficiency and my temperature for my Carnot cycle with ideal gases. So do we have any questions before we move on into calculation of the efficiency of the Carnot cycle? No? Okay, we're happy. Let's go. So again, I listed some useful information for you. You should also like organize these relationships in somewhere you can find so you can quickly identify them. So when working on the efficiency of my Carnot cycle, there are a few things we want to know. So first of all, we want QC and QH. It's not very straightforward. What is my QC and QH and how to calculate my QC and QH in this picture. So let's set up from using what we know. What do we have? We have our first law of thermodynamics. That is delta U equals to Q plus W. All right. Rewrite our delta U equals to Q plus W. We got the following equation. Now delta U equals to CV dt for ideal gas. The Q will stay the same. Or this one, actually, we can rewrite it as du equals to dq equals to dw plus dw. Now dq will remain the same. My dw, since my Carnot cycle is reversible, we can replace that to be negative PdV, or for ideal gases, that's negative nRT over V dV. So far, so good. We're just rewriting our first law of thermodynamics. Now, the expression we got is CV dt equals to dq minus nRT over V dV. So in order to do further operations on this equation, I want to move my temperature onto the left-hand side, at least move my temperature with the dt, right? So I'm going to divide both ends by temperature to get CV over T dt equals to dq over T minus nRV dV. okay? And then, since we have a cyclic process, let's just take the integral for all 4 steps, like 1 to 2, 2 to 3, 3 to 4, 4 to 1. Those integral add up. We're just going to do a cyclic integral of Cv over T dt equals to a cyclic integral of dq over T minus cyclic integral of nr over V dV. And then observing these integrals we set up, these 2 integrals are called ordinary definite integral. You don't have to remember that, that's your math. Definite integral. Effectively, what does ordinary definite integral mean? Is that we only have, say, one variable, and we're taking the integral of that one variable. Now, for any ordinary definite integral, the cyclic integral of any function like fx dx will equal to 0. This is also quite straightforward to understand. If you think about if I only have like any function, as long as I only have one variable, you can solve it to some kind of function by solving the non-definite integral, right? And then since we're taking the change in the same variable, now for a cyclic process, the change of this dx will vanish at the end, so this entire integral will vanish. So using this calculus information, going back to the expression we did, remember this one, the only thing we're doing is the first law of thermodynamics. Write out expression of the first law of thermodynamics. Doing the cyclic integral on both ends, what we have in this one, we only have one variable, which is volume. This one, my heat capacity. For ideal gas, my Cv is a constant. For non-ideal gas, my Cv is a function of temperature. But nevertheless, on this one, we only have one variable, which is temperature. So using our simple calculus, we can write out this one to be 0, this one to be 0. So my center part must add up to 0. Or what we have is writing out my cyclic integral equals to the process between 1 to 2 dq over T plus 2 to 3 dq over T plus 3 to 4 dq over T plus 4 to 1 dq over T must equal to 0. All right. And if we pause here and thinking about what we discussed last time, is whenever you have a function, whatever function it is, as long as its initial and final states are the same, you have a state function. So in this case, by taking the cyclic integral of something inside, we find that my dq over T is the state function that will vanish. I call it like Carnot for now. Effectively, it doesn't necessarily to be Carnot, but it must be reversible. But let's just call it d Carnot for now. So what we find out by analyzing our Carnot cycle is that there must exist a state function, which is the infinitesimal change of my d Carnot over T. So this is going to be my state function. We'll come back later on to make this more general and give a real definition of entropy. So this is how scientists start to recognize, okay, we need one more state function to discuss our thermodynamic properties. Before we have internal energy, we have enthalpy. We also have like pressure, volume, and temperature. And this represents another state function that we need to define. All right, nevertheless, we'll talk more about the entropy and definition of entropy in our next lecture. But for now, thinking about what we have these four integrals adds up to be 0 for the cyclic process. But if we go back to our Carnot cycle, we know that 2 out of the 4 processes are adiabatic. Whenever we have an adiabatic process, we know about the dq. Right? So for these 2 processes, my dq between 2 to 3 and 1 to 4, my dq is 0. So in here, between 2 to 3, this one is 0. Between 4 to 1, this one is 0. And it is 0 because we know these 2 processes are adiabatic. All right, so we simplified our relationship into 1, 2 dq over t plus 3, 4 dq over t equals to 0. And what do we know about the process between 1 to 2 and 3 to 4? They are the same temperature, right? So for the process of 1 to 2, the temperature is always kept at TH. So we can replace this temperature, and since it's constant, I can take it out to be 1 over TH between 1 to 2 dq plus 3 to 4, and take the 1 over TC out and dq. And they add up to be 0. And now taking this integral becomes very straightforward. It only have a dq. So this comes out to be qh over th plus qc over tc adds up to be 0. Remember what we are trying to do here. We're trying to find an expression of our efficiency of the Carnot cycle. Now in the definition of the efficiency, we have QH over QC. So we just want to simplify this expression into QC over QH. That equals to negative TC over QH. This is just moving terms. And then plug this one back into our original equation. We have the irreversible equals to 1 minus TC over TH. And we want to write this is for Carnot cycle ideal gas. So what's the physical meaning of this equation? It tells us we have an expression for the efficiency of a Carnot cycle containing ideal gases. And in the meantime, while solving for it, we find out there must exist a state function, which is dq Carnot over T. Any questions? Right, so we start from the second law of thermodynamics, went over what is a heat engine, went over the discussion about Carnot principle that a reversible heat engine is the most efficient one. And then we built a reversible heat cycle, right? So this is a cyclic process. We have an isothermal process followed by adiabatic, followed by isothermal, followed by adiabatics. And that process is this cycle is defined as a Carnot cycle. And then by analyzing the Carnot cycle, we find out there must exist a state function, dq over t. We'll talk about that in our Friday lecture. And then by using very simple calculus, we have an idea about like this one is 0, and that's why we know it's a state function. And later on, we know the 2 of them are adiabatic. So we have a way to link QC and QH with TC and TH. And that goes back to calculate the efficiency of the Carnot cycle. And how do we use this equation in an example question? So let's do one example question together, and there's another one you can try it yourself. So reading it, it says, suppose the coldest reservoir we have in hand is 10 degrees Celsius. And we want a heat engine that is at least 90% efficient. What is the minimum temperature required for the hot reservoir, assuming we're talking about a Carnot cycle with ideal gases? Sometimes your textbook drop assumptions. So in our exam and problem set, I want to make sure we have all those assumptions there. So how do we set up the problem? It tells us the coldest reservoir we have in hand is 10 degrees Celsius. So my Tc equals to 10 degrees Celsius or 283 Kelvin. My E maximum equals to 90%. And we know the maximum efficiency is reached when it's reversible. And that's why we're using our Carnot cycle as our reversible engine. And this gives us, this equals to irreversible, which equals to 1 minus Tc over Th. And then we can just plug in the numbers. So 0.9 equals to 1 minus 283 Kelvin over Th. So keep in mind, always translate your temperature into Kelvin. It doesn't hurt. And then we can solve for our Th. And this one is just 2830 Kelvin. All right. So this part will serve as one of something I call like short answer problem in your exam. So typically in your midterm exam, I'm expecting like 10 true and false problem, and then 4 short answer problem, and then 2 like comprehensive problem, like with multiple parts. So a problem like this will serve as a short answer problem in your exam. I will post my previous midterm exam for your practice, but please be noted, my previous midterm exam is way longer than I hoped it for. So it's going to be slightly different and shorter this time. But nevertheless, that's the end of our today's lecture. See if we have questions before we leave. We have 2 more minutes left. No? Okay, well, I'll see